So in this video, I'm going to go through the derivation for what we call the integrated rate laws that we already have for reaction A makes products, the relative rate expression where we could say that the rate of the reaction equals negative change in A over change in T. And again, the negative sign is because it's a reactant, and then change in concentration over change in time. And then we also have what we have been calling the rate law, but it's really the differential rate law, where it's rate equals rate constant, and then times the concentration. And if we're talking about a zero order reactant, then it would be to the 0 power, and if it's to the first order, it's a 1 exponent, and if it's second order, it's a 2 exponent. So this could be 0, 1, or 2, depending on what the order of the reaction is with respect to A. Now, first, we're going to go through this process for zero order. And again, we're going to assume that this is A makes products. Now, the rate law, if it was zero order, would be just rate equals K, because again, this is concentration of A to the 0 power. So it's just rate equals K. Now, for the word rate, we're going to write in what the relative rate expression would be with respect to A, our only reactant there, which means we'll have negative change in A over change in T, and then equals K. So we just did a substitution for the word rate. Now, we're basically going to take the differential rate law and turn it into an integrated rate law, which means we're going to integrate. So we're going to do separation of variables, integrate the left and right sides, and evaluate. So I'll have negative integral of change in A over change in T, and then K integral change in T, and I'll go ahead and change these triangles into D's, so it's dA and dt, and we're going to evaluate both sides from 0 to time t. So on the left side, we simply get negative concentration of A evaluated from 0 to t, and on the right side we get K of T evaluated at 0 to t. So on the left side, we'll just get negative concentration of A at times T plus concentration of A initially, and on the right side we'll just have K, and then this is T minus 0, which is just equals to KT. Now just a quick little side note, this part, A at times 0 or A initial, sometimes we might call that, A naught. That's how it's spoken. And it just means, in this case, concentration of A at time equals 0, or the initial concentration. So anytime you see a little subscript 0 on something, it's usually the initial something, like initial velocity or initial time, or initial concentration in this case. So next thing what we're going to do, actually let me add one more step. So negative concentration of A at times T plus concentration of A initially equals KT. Now we're just going to rearrange this a little bit so it takes on a y equals mx plus b format, which means we'll have concentration of A at times T equals negative KT plus concentration of A initial. And then this is what we call the zero order integrated rate law. And again, it takes on this y equals mx plus b format, where m equals negative k and b equals the initial concentration. So if we were to make a plot of concentration versus time, we should get something that's linear, and it might look something like this. So it's linear, where the slope of this line equals negative k. So now we're going to do this again, but now with respect to first order. So we're going to pretend that we have a first order reaction now. We're still talking about A mixed products. So the rate law, since we're saying it's first order, is rate equals K times concentration of A to the first power. And the relative rate expression, so what we're going to substitute for the word rate right now, same thing as before, negative change in concentration of A over change in time. And on the right side equals K times concentration of A. So same thing as before, we're going to separate our variables and do an integration, which means we'll have negative integral, which is going to be evaluated from 0 to t, and then actually change it to d's instead of the change in, so dA dt, or sorry, dA, and then concentration of A down here, and then over on this side we'll have K integral dt, also evaluated from 0 to t. So then remember that if you have integral of 1 over x, that's natural log of x, so we're going to use that here. So we'll have negative natural log of the concentration of A evaluated from 0 to t equals K t, essentially, because we had t evaluated from 0 to t. So then we'll have, on the left side, negative natural log of concentration of A evaluated at time t plus natural log of concentration of A at initial equals KT. And then just rearranging this a little bit, so we have y equals mx plus b format. We'll have natural log of the concentration at time t equals negative KT plus natural log of the initial concentration. So again, this takes on a y equals mx plus b format, and we're going to call this the first order integrated rate law. And because it's y equals mx plus b format, if we were to graph this, again, notice that m, the slope, must be negative k, and b, the y-intercept, must be natural log of the initial concentration. So if we plot natural log of concentration versus time, we will get a line, and it would look something like this. It's linear, or the slope equals negative k. Now, what if, and this is not something that's usually in the textbooks, I don't think it's in our textbook, but what if the reaction was actually 2A makes products? How would that affect our derivation? So our rate law would still look like rate equals K times A to the first power, because we're still assuming it's first order. But now our relative rate expression is a little bit different. So the next step, instead of, so I'm looking at this part that's changing, instead of negative change in A over change in time, we'll have negative 1/2 change in A over change in time. And this equals K times concentration. So that's the difference so far. Now I'm just going to quickly go through what happens in this case. We'll get a slightly different result because of that 1/2. So we set up our integral, we'll have negative 1/2 integral of 1 over A, and then the dA. And then on the other side, we'll have K integral of dt, and both of these are still being evaluated from 0 to t. So then after we integrate, we'll have 1/2 natural log of concentration of A at times t minus natural log of concentration of A at times 0 equals KT. And then simplifying a little bit, natural log of concentration of A at times t minus natural log of concentration of A at times 0. So I'm moving the 1/2 over to the other side. So now I have a 2 KT. And then rearranging so it takes on y equals mx plus b format. Natural log of concentration of A at times t equals negative 2kt plus natural log of concentration of A at time 0. So the key difference here is our slope, m, equals negative 2k. Sorry, not the t. Slope equals negative 2k instead of just negative k. And then the y-intercept is still the same. That's still natural log of the initial concentration. But if we were to plot this one, natural log of concentration versus time, obviously we'll still get something that's linear, but the slope of this line is negative 2k instead of just negative k. And again, that part's not normally in the textbooks, and College Board knows that. So if you had a reaction on the AP exam where it was, 2A mixed products instead of just A mixed products, and you remember this, they would give you credit for it. If you forgot it, they'd still probably be okay with it. It did come up in an FRQ not too long ago. Anyway, let's do this all again, last time, but now second order. And again, we're assuming it's A mixed products. So we're going to start off, same thing that we always have with the others, the rate law, which if it's second order, is rate equals K times A to the second power because it's second order. And then for the word rate, we're going to fill in the relative rate expression for A, which is negative change in A over change in time. And then on this side, we'll have K A squared. So separating our variables and getting ready to do the integration, we'll have negative integral, and we'll have 1 over A squared with the dA. And over here we'll have K integral of t, both of these being evaluated from 0 to t. And then recall that the integral of 1 over x squared equals negative 1 over x. We're going to use that to evaluate our integral, which means we'll have 1 over concentration of A, the two negatives canceled out, evaluated from 0 to t, and on the other side we'll have kt, because it's just t evaluated from 0 to t. So then we'll have 1 over concentration of A at times t minus 1 over the initial concentration of A equals kt. And now rearranging so it takes on that y equals mx plus b format, we're going to have 1 over concentration of A at times t equals kt plus 1 over the initial concentration. And this is what we call the second order integrated rate law. And again, because we set it up so it takes on y equals mx plus b format, that means the slope is k, and the y-intercept is 1 over the initial concentration. So if we were to plot this one, where we plot 1 over the concentration versus time, we might get a graph that looks like this, where linear, it's and slope equals k. And then let's do our hypothetical again. What if it was 2A mixed products? We get kind of a similar result. So we still have the rate law equals K times concentration of A squared. But this time when we set it up with our relative rate expression being substituted for the word rate right here, we'll have negative 1/2 change in A over change in T equals K times A squared. And when you set up your integral, you'll have negative 1/2 integral of 1 over A. So it's very similar, we just have that 1/2 in there. So 1 over a squared dA equals k dt, integrating from 0 to t on both sides. And we end up with essentially, I don't want to skip too many steps, but 1/2, and then 1 over a, because again, we're using that same rule for, or that same guideline for the integrating value from 0 to t. This equals kt. And then when you rearrange, we'll have 1 over, so rearranging to include it into to turn it into one, y equals mx plus b format, we have 1 over a at time t equals 2 kt plus 1 over the initial concentration. So again, the difference now, our slope equals 2k instead of just k. And if you were to plot this, 1 over concentration versus t, you still get a line like this, but now if it's linear, the slope equals 2k. And again, that's a minor detail that's not really in the textbook, but I just wanted you to be aware of it. Now, what's the purpose of all of this? Well, when we do the crystal violet lab, which, when I film the data for you and give it to you, but when we do the crystal violet lab, you're going to get a bunch of data of concentration changing over time. And a chemical reaction can't be 0 order and 1st order and 2nd order. It's only one of those. If you were to take your data and plot it 3 different ways, so concentration versus time and natural log of concentration versus time, and then 1 over the concentration versus time, only one of these methods of plotting is going to actually make it linear for you. So that's what you would do with your data, is you would plot it 3 different ways. And maybe concentration versus time might look like this, and natural log of concentration over time might look like this, and then 1 over concentration over time, I don't know, maybe looks like that or something. But the point is, only one of these is going to be linear. And this one, with my quick example, that one is obviously, of the 3, the one that's linear. So then that would tell you it's 1st order with respect to A, whatever you were plotting. Only one of these is going to end up being linear. So you take your data, you make 3 graphs, and whichever graph is linear or most linear, that's going to tell you the order of the reaction with respect to whatever you were graphing.